Hey guys, hello everyone. Welcome to Rasayan Academy, all of you once again. So in this particular video, we are going to be discussing questions on heterocyclic reactions. Right, so this topic is divided into two parts. That is, one is the synthesis of heterocyclic compounds, which usually covers simple compounds like pyrrole, furan, thiophene, and fused compounds like indole, quinoline, isoquinoline. So most of the times only these few are asked, their synthesis as well as their reactions, along with pyridine definitely. And even if you find synthesis boring, you must at least see how these kind of molecules react, because the reactions are very similar. And the reaction, by which position they are going to do electrophilic aromatic substitution or nucleophilic aromatic substitution, at least you must be able to understand that to be able to answer questions, because no topic in organic chemistry is asked separately. All the questions are mixed with different topics. Okay, so yeah, let's start and practice a few of these question, important ones. Right. All right. So what is the major product in this question? Now this is a very simple one. Just let's try and answer this one first. Try it on your own. All right. We have a substituted pyridine. Okay. So anything is going to happen to the substituent when we are taking H2O2? No. This peroxide is specifically used. See, what is the kind of nitrogen atom? See, this lone pair on the nitrogen atom does not involve in resonance within the ring, right? That means you are going to use this lone pair for attacking the oxygen over here. This is how the peroxide is. Alright, if one of the lone pair attacks on this oxygen, this OH minus is going to eliminate. Alright, that means here you are actually getting this kind of a oxidation. What do we call this? We call this heteroatom oxidation. We call this heteroatom oxidation. Alright. Now what is next? Next is PCl3. What is the PCl3 used for? See, PCl3 has phosphorus, and definitely phosphorus has vacant d orbital even though it has a lone pair. But since it has a vacant d orbital, it is going to accept electron density from oxygen. Oxygen has a huge affinity for phosphorus, isn't it? So yeah, how are they going to bind? In this way, OPCl3. See, this is going to have a minus charge, so it is going to replace one of the Cl. So that Cl minus, what is the Cl minus going to do? The Cl minus knows that I cannot attack over nitrogen because nitrogen has a positive charge, but it cannot attack over nitrogen because it does not have a vacant d orbital like phosphorus. So chlorine is rather going to attack over this carbon and release this electron density so that the nitrogen does not have a positive charge anymore. So what just happened, guys, that pyridine, when the nitrogen becomes positive, pyridine is going to face the attack on the adjacent carbons to nitrogen. Why? Because nitrogen itself cannot accommodate one more atom, because it does not have enough vacant orbitals. That is why it is going to make the adjacent carbons more electrophilic. So now you have a two substituted pyridine, and it is not exactly pyridine because there is a hydrogen over here. Now what happens is this hydrogen is going to fall off in this way. This whole thing is going to eliminate, and you are going to have 2 chloropyridine. Alright, you are just going to have 2 chloropyridine. Now what is next? Definitely the water is just to do the aqueous workup. It is not having any particular role as such. So B is going to be the correct answer over here. Very simple and easy. Let's move onwards with the next one. Now what is the major product in this particular question? You have furan, and let's see what are these three reagents going to do with furan. If you have studied from any standard book about heterocyclic compounds, you will know that furan is least aromatic as compared to thiophene, as compared to pyrrole. Thiophene is the most aromatic and the ring is very, very stable. Pyrrole is also more aromatic as compared to furan, but furan is the least aromatic, and that is why many times, many times you will see it does not undergo a simple substitution reaction. Rather, sometimes it is going to add to this whole system. If it is going to add like this, then what will happen? Or let's say I'm saying that the oxygen is pushing electron density to add the bromine. Okay, no problem. If that is the case, it is going to become something like this. ये देखो, there's one bromine, there's one hydrogen like this. Positive charge, very well. But now what? How is it going to get back the electron density? This Br minus, it is not going to remove the proton and gain back the aromaticity because it's not so powerfully aromatic. Alright, so what happens next? Acha, ek aur cheez guys, I have missed this out one thing, because always remember it is going to attack from the 2 and the 5th position. So yes, if you were doing it like this, that I want to make the attack from the 2 or the 5th position on Br positive, or let's say delta positive, then it is absolutely correct. You are going to have to write it like this: bromine, hydrogen. So first priority is going to be the 2 and the 5th position, and then if they are occupied, you will have the 3rd and the 4th position. Alright, chalo. So we did this. Now what? Is the proton going to be lost and it is going to regain the aromaticity? No. There is a nucleophilic solvent over here, as I can see. So that nucleophilic solvent is going to attack. Okay, तो मतलब कि it is not regaining the aromaticity because the furan aromaticity or stability is the least. Now what happens? The bond is going to fall on this oxygen, and you are going to get OMe and Br. It is no more aromatic. Alright, so now we can break the ring also. How are you going to break it? In the presence of hydrolysis, you are just going to hydrolyze this molecule. So after hydrolysis, what are you going to get? See, after hydrolysis, these two bonds are going to break apart. And when that happens, you will get like a diol. OMe, OH. This is what you're going to get, because definitely water is going to attack at one of these position. Bond is going to open up both sides. You're going to get OH. Right, but that OH, the bond is going to release and remove the good leaving groups. These are all good leaving groups. So Br is also a good leaving group. So ये इसको निकाल देगा. And it would prefer to form the aldehyde. What aldehyde is this? It is 1,2,3,4 dicarbonyl compound. Now what happens next? What is this molecule that you have? This is nothing but a phosphonium ylide. This is an ylide. So what are we going to do with the ylide? Ylide is going to react. Alright, and how is it going to react? It is going to give you a Wittig reaction. Wittig reaction means any one of these aldehydes is going to do a Wittig reaction. And here, it's not mentioned how many moles. So let's say I'm just using one of these, because then the number of carbons would be huge. So I'm just doing a Wittig reaction on one of these. So let's say this is it. And it is not a stable ylide. It is not a stable ylide because you have O minus. It is not taking electron density, it is giving electron density to this alkene. So this ylide itself has a aldehydic group. That is why we have written it in this manner. But anyways, just understand that over here, this carbon is attached to this aldehydic carbon. This one is attached to this aldehydic carbon, and this is your CHO. So what do you ultimately get? You actually get this molecule, option number B. This is what you are going to get, option number B. But in this scenario, you're just keeping on adding. Alright, you're not removing methanol, you're not removing, this water. If there is a little bit amount of water over here, especially for 1, 2, 3, 4, 5, 1, 5 dicarbonyls like this. What happens? Let me show you. When I suppose that I have option number B as the correct answer, which has one cis and one trans alkene, I would say ki, yeah, this is my correct answer, no problem. But there is a problem. What is that? If I just do this kind of a protonation, then what will happen? This double bond is going to shift away. Yes, and that double bond can become this kind of a enolate like intermediate, isn't it? Now it has become a single bond. I think this is going behind me. Anyways, this is going to become a single bond over here. It can cause rotation. When it causes rotation, it can cause isomerization. Alright, a positive over here. So this molecule does not end up like this. After isomerization, it is going to become option number A. And does it always happen with all the molecules? No, I cannot say so, because all the molecules will not do isomerization. But here, since you're having a CHO on both the ends, it is possible. It's like a complete resonating structure. Alright, completely resonating structure. See, within the CHO, this bond is going to go, and after isomerization, it will try to form a more stable compound, which is a trans alkene. Alright, completely resonates. So A is going to be the correct answer. Alright, chalo, let's move onwards. And also reminding you all, even if you don't have a proton, let's say, suppose even if you don't have a proton, still after resonance it can do the isomerization, okay, to give the major more stable product. Moving onwards to third question over here. So you have a furfural molecule. Now the aldehydic, the 2-formyl furan is also known as furfural molecule. This has to react with two of these reagents. What is going to be the major product? Yes, the reactions of furan, especially in the presence of acid, there is a huge chance the furan is going to open up. And that is what we see in two options. And in the other two options, furan is not disturbed. So let's check what is going to be the correct answer. First thing, I see that there is a methyl lithium, which is a very strong base. So what is that going to do? Let's see what combination is possible. I can spot a phosphine and an alkyl halide. As soon as I can see this, I know there is going to be an SN2 attack. So this is the kind of molecule that you're going to get first of all. Now phosphorus gets a positive charge. Now methyl lithium, because the phosphorus having a positive charge, this carbon is going to become electrophilic and the proton will become acidic. That's why methyl lithium is going to convert this molecule into a stabilized anion, and that is exactly what we call as a ylide. This has become a phosphorus ylide. Now what the phosphorus ylide is going to react with CHO, that's it. And how does the molecule look like? It is going to give you a Wittig reaction, and this is a stable ylide, so it is supposed to give you a trans compound like this, right? It is supposed to give you a trans compound. So is the option going to be option number A? No, wait, you still have hydrolysis. Now how does hydrolysis proceed with this molecule? As soon as you provide any kind of electrophile to it, it is going to do the same thing as you saw in the previous question. Just like you did bromination, this is how it is going to happen. Alright, and methanol is going to attack then. ये तो दोनों हाइड्रोजन लग गए इस साइड पे. Now methanol is going to attack. Actually, I think that it is going to attack from this carbon and methanol attacks over here, such that you get a less hindered compound, yes. And also the flow of electron density is towards the more electron withdrawing group, yes. So that's why we should move it on the other side. We should move it on the other side because this is where the flow of electron is going because of this electron withdrawing group. Alright, so we try the same thing over here, this side. And now there is a hydrogen. So what is the methanol going to do? It is going to open this system. Yes, and it has now become OME, double bond CO2Me. Now what is going to happen? Again, there is water. Water is also present over here. So what is that water going to do? It is going to break the whole system, and it is finally going to give you option number D as the major product. All right. So sorry, option number C. Yeah, because there are two ester groups over here. So this whole system is now going to open up. And as I told you, whenever, this is the formation of furan also takes place, a very common reaction if you have heard of it, Palnor synthesis. So Palnor synthesis simply uses 1,4-dicarbonyl, 1,2,3,4 dicarbonyl, puts some dehydrating agent or like a Lewis acid and closes the ring. If I just provide acid to the furan, it is going to break down to 1,4-dicarbonyl. So if this molecule breaks down to 1,4-dicarbonyl, it is going to be a ketone on this side, because already a substituent is present, right? And on the other side, it will again become a ketone. But this ketone, like this ketone is actually going to have a OH group. Alright, so yeah, what happens next? This proton is going to fall off because there is a conjugation, and you are finally going to get this molecule. Alright, so C is the correct answer. Now, yes, both the reagents are used. C is our correct answer. Furan is very easy to break. Next good question. Again furan. Yes, try it out. What do you have? One very important reaction of furan with any strong base like butyl lithium is this. That is, whenever you see furan with butyl lithium is there to remove a proton. From where it is going to remove a proton? Definitely it is going to do a ortholithiation. Alright. It is going to do ortholithiation. That is, it is going to be like this, that this is lithium, this is butyl. So it is going to, because of the chelation with lithium, it is going to pick out the nearest hydrogen, or the nearest proton, and that is why you have a negative charge over here. This is where you have a negative charge. Now who is the electrophile? It is going to attack over here simply. So I can just add it. Second reagent use kara, and I'm going to just add it over here. This ring is going to be as it is. What is this? Just a toluene ring. Okay. Now what, guys? Again, you have water and you have a proton. So when you have nothing like methoxy or anything, you just methanol nahi hai, sirf plain water hai. So the plain water is actually going to break it down in the presence of acid into a 1,4-dicarbonyl system. This is one carbonyl, this is another carbonyl. Just exactly, we have done this plenty of times, so by now I think you should understand how it has formed. Okay, the same method. So 1,4-dicarbonyl formed, furan is gone now. Next step is base. Whenever you have this kind of a carbonyl compound and there's a methyl to do enolization, and you have a base also, definitely it is aldol reaction. So I'm going to remove a proton from this. It is going to cause enolization followed by the attack on this one. Why not this proton is removed? Yeah, we can try that also, but first let's see this possibility. I'm writing the carbonyl outside. This is going to be a 5-membered ring. Right, like this. This is one possibility. This proton is going to be lost. And here you have this carbonyl and the ring on the 1 and 3 position. So do we have any option? Do we have any option where you see the carbonyl and this aromatic compound is on the 1 and 3 position. After elimination, it is going to give you this kind of a system. Yes, have I written correctly? Yes, I have. All right. So this is one product which forms, and the other product is, the other possibility is that I remove the carbon, remove the proton from over here. What is this? This is a benzylic as well as a alpha proton. The benzylic proton is supposed to be more acidic because the enolate which forms is going to give you like a more stable one. So चलो ये भी try कर लेते हैं. I'm writing directly aromatic compound. So if this attacks over here, the bond is going to open up. After losing water molecule, it is going to become something like this. Right, so B is going to be the correct answer because here you have the aromatic group on the second position, alright, and the methyl is on the third position. This is correct and not this one. Why is that so? Because we will use these protons and that is going to lead us to this product, and this is, even if it forms, it is only minor, and this is going to be the major one. All right, so I hope that you are also getting the same product and liking this mechanism. Now we move onwards to another important question. Yes, this is another very important and a tricky question. Try this out. Alright guys, so if you have tried out, let's understand what's going on over here. So first thing is, whenever you are having this kind of a molecule with sodium bicarbonate, this molecule, it's a imidazole type molecule, you have only one proton to be lost. So let's say the sodium bicarbonate is removing this proton, after which it is going to become a nucleophile. But where is it going to attack first? Let's say it is going to attack on this carbon first because Cl- is a very good leaving group. Alright, so that is a better choice of attack, and also it is going to be a really good SN2 reaction because, as you already know, in the SN2 reaction, if on the alpha carbon or the adjacent carbon there is a carbonyl or some electron withdrawing group present, that is going to give you a very nice SN2 reaction. Alright, so this ring, this nitrogen is going to first attach over here. This is the first thing. What is the second step? I can see that you have this kind of a sulfoxide. You have three methyls. One methyl I'm writing as CH2H. Why so? Because there is also OH minus, and if you have seen the Korey-Chaykovsky reaction, you will know what is going on. You will know that this is a sulfoxide, not a just simple sulfide. It is a sulfoxide, which on conversion to ylide is going to give you a more stable product. So, however, you don't have alpha beta unsaturated carbonyl. This is the Korey-Chaykovsky reaction. So you only just have this carbonyl. So what is it going to do? It is just going to form the epoxide out of the carbonyl, nothing else. Alright, so this is just forming epoxide. Inserting this CH2 over to this. Alright, so this carbon is still attached over here. Alright, you just have to know few things and remember them. Like this is a Korey-Chaykovsky reaction. Now third attack. see, again you are having a mild base to remove this proton. So if this proton is removed, now the nucleophile is going to attack on the less hindered side of the epoxide, definitely. And what is the product going to look like? It is going to look like this. I'm not going to draw it again and again because it's not possible. After one more nucleophilic attack from the same molecule, this is how it is going to look like. Alright, so yeah, a symmetric product. Chalo, let's move onwards. What is the major product over here? Now this is an indole molecule, and let's see how these two reagents are going to react. Very, very simple question, too easy. So, you must be able to identify what is going on. You are having a secondary amine and you are having a formaldehyde. So this is absolutely going to form this kind of a iminium ion, which is also known as the Eschen-Mosher salt. Yes, why is it so popular? Because it is used in Mannich reaction, isn't it? This is going to be a Mannich reaction, Me2N double bond CH2. Nitrogen has a positive charge. This is indole. So indole will always attack from the third position, not 2 and 5. Because if it attacks from the second position, it has to disturb the aromaticity of benzene. So without disturbing benzene, it is only going to attack from third position like this. One proton, one CH2, NMe2 like this. Still positive on nitrogen, this is going to fall off and it regains aromaticity because this is an aromatic compound. Alright, so we write the final product. This is how it is going to be. CH2NMe2, 2 methyls. Now in the last step, what is the last step? Sodium cyanide. Now, there is one more thing. If I just add sodium cyanide, cyanide is going to attack over this carbon and replace it. But there is one more important thing. If I just provide one more methyl iodide to this molecule, that is going to make, it's not mentioned over here, but I'm just mentioning this to you, that if I just have one more methyl, that methyl is going to be taken quickly by the secondary amine. It becomes NMe3 positive and now it becomes a very good leaving group. And now if you're providing the sodium cyanide, it is going to quickly attack and this is very eager to leave. What is going to be the major product? Option number D. Just a simple substitution of this amine group by a cyanide. So first we had the Mannich reaction followed by a simple SN2 substitution, which would be better if I provide the methyl iodide and convert the amine to a quaternary ammonium ion, which will finally end up like this. This is a better leaving group than NMe2 minus. Alright, so this is the leaving ability. That's why I have given you this methyl iodide in between. Okay. Yeah, guys, little things make a lot of difference. Chalo, next question. What is the major product? Alright guys, if you have tried out this question, it's a very simple one. So what we're going to do first of all is, that there is hydrazine and it is going to open up this anhydride by attacking on the carbonyl. It's very simple. Now that is okay because you are going to get something like this in the first step. But in the second step, again, the hydrazine, the second nitrogen of the hydrazine can do the same thing and it is going to finally give you a 6-membered ring. Alright, so that is going to have both the sides, these two NH groups. The hydrazine has actually inserted into this molecule, replacing oxygen as a water molecule. Definitely there is going to be like acid, even if it is not given, you can simply do this mechanism, not a problem. Now what is the role of POCl3 over here? POCl3 is here to basically remove this oxygen, as soon as you see that there is a oxygen and a phosphorus, definitely they are going to react. So this is how the molecule is going to become after a while. And now the free Cl minus, you can just first remove this. That is how it works. because then only the molecule is going to be free. Alright, and also this is a bulky group, so you cannot just directly do a SN2 reaction, no. So you have to go through this mechanism, right? So Cl minus is now going to attack over here and open this bond and do the substitution. Alright, this is how it works. There is a Cl. Now again, trying out the same mechanism. You can do the same mechanism. One more POCl3 you can use. One more mole of POCl3, that is going to do the same thing. Alright, it's going to replace the lower oxygen. Why are we replacing these oxygens? Because we want this position to be free to be easily attacked by let's say some nucleophile. What am I doing? There is no double bond yet. It is not having a double bond yet because it is still NH groups. I have not aromatized the molecule completely, no. So what next? Next is ammonia. Then I see alcohol molecule. So these are the nucleophiles which we want to add to this molecule. First we add ammonia. You know, that is why the oxygen was removed, so that ammonia can easily react. See how it is going to happen the same way. First the Cl minus is going to move, and then the ammonia is going to attack. So you finally get the amine group in the molecule, NH again. Alright, this is still a Cl, no problem. In the next step, you are going to have the alcohol. So alcohol, there's a base with the alcohol, strong base, like alkoxide or something. That is going to remove this proton and again eliminate the Cl in the same manner. Alright, don't just directly do a SN2 reaction. This is not an SN2 reaction. It is like a aromatic kind of a substitution. Okay, addition elimination mechanism, or I should say elimination and then addition. Yes, elimination then addition. Now you can see a base is present, so base is going to remove both of these protons and then it can make the molecule aromatic. So C is going to be the correct answer. Alright, so I hope that you have tried out and got the same answer as well. Here it is. Try it out, guys. Very simple. Alright guys, so it might seem like a very tricky question. Let's see what's going on. You have HCOO minus. So what is that HCOO minus going to do? As long as you have an electrophilic position, it is just going to attack. That's it. Now what is next? You are going to have Br minus and ammonium ion. So ammonium ion is definitely going to provide a proton over here. Then later on ammonia can attack on this carbon. So I'm just going to do iminium ion formation directly. Followed by which there is going to be a cyclization in this way, and I'm directly writing the final molecule because I think you will be able to do this on your own. So this is how the cyclization is going to give you this molecule. Alright, now what happens next? Next you are having an alkyne. So what is the alkyne going to do? The alkyne is going to react with this molecule. Alright, now what is going to be the stereochemistry? The products are already given. There are plenty of options which are given. So we will try out both of these possibility. One possibility is like this. So guys, this is the most stable possibility actually. Why? Because here the here the cyanide group is going to leave, which is the most stable form of a leaving group in a retro-Diels solder reaction. Alright, if I just make this alkyne group leave, it is not going to make sense. The reaction will go backwards. So if we have to move this reaction forwards, this is how it is going to be. And this is how your product is going to be. I've just got to make a correction. Option number D is going to be like this. There is no nitrogen over here. This is a perfect way. This question has been asked in your examinations also, but I just have added one more step. It is a question from the books itself. So in your examination, this heterocyclic ring and this alkyne was given and you just had to form this furan. But that will be too easy, right? If I don't give you this one step for the formation of this heterocyclic, it will become very easy. And nowadays, it's not very easy to answer questions. So you have to think a step ahead. Now D is going to be the correct answer. And yes, there is not going to be any heteroatomic molecule or heteroatom present in the final product. It is going to be a simple furan. So just star mark this one, very important and interesting too. Let's move onwards to next interesting question. Again, furan you have. Alright, try this out. Alright guys, let's start answering this question. It's very simple. So in the first case, what's going to happen? There is LDA. LDA is going to do ortholithiation, alright, because that is going to be the favored thing. This proton is going to be more acidic as there is also a bromine group attached. So I will remove this proton from this side. And what is next? Next you are going to have this allylic bromide which is going to open up. So after the allylic bromide is removed, it is going to become something like this. And there is a bromine over here. Alright, so after that, if we are using butyl lithium, that butyl lithium is going to do a halogen exchange and bring the lithium over here. So you are going to just have the methyl group over here. And the final product is like this. So the question is just a simple question based on selectivity, nothing else. Just a selectivity question. Alright, so first when you are taking LDA, it is only going to give you a butyl, it's only going to give you a proton removal, and this first electrophile is added on this position. Second base, this is going to do a bromine exchange faster than taking the proton. That's why it is selected for removing the bromine from over here. So the answer is going to be option number D. Alright, so let's try out another question. Alright, so I think that you have tried it out. Alright, now this is a very simple question. You are doing nitration. Okay, so which ring the nitration is going to happen? This pyridine ring or the benzene ring? Definitely guys, pyridine is an electron deficient ring. It cannot undergo the substitution electrophilic aromatic reaction. That can only be done in benzene. So that's why benzene is going to undergo nitration. But where? On the para position, para to pyridine, definitely not. Ortho to pyridine, again not. Why? Because both the ortho and para position, both of these positions are going to be rendered electron deficient by the minus R effect of pyridine. Pyridine is actually having a minus R effect. Alright, in this way. Positive. In this way, and this charge is going to go over here. So both the ortho and the para position are electron deficient. Yes, with respect to the electron withdrawing pyridine group, the meta position is the most favored. So C is going to be the correct answer.